What if I told you that the invisible forces shaping your daily life were born from a simple idea proposed centuries ago? From traffic lights to your social media feed, to how Netflix knows exactly what you will watch next. The name of this silent engine driving the modern world is algorithms. Behind these digital instructions, which we often do not notice, but which guide our every moment, lies a surprisingly deep and ancient history. Born from prophecies, astronomy, mathematics, and mechanical clocks, this concept evolved over centuries to become one of the most powerful structures defining our 21st century existence. Now, it is time to discover the secret origins and evolution of these invisible architects that create the true magic of the modern age, and to explore how they are reshaping our lives today. In the modern world, many movements, decisions, and recommendations around us are shaped by the silent functioning of an invisible mind. From the rhythm of traffic lights to a social media feed, from a music app predicting the next song to banks calculating credit risk, every process is part of an orderly system controlled by algorithms. Algorithms speak a language most of us are not even aware of. This language consists of step-by-step instructions designed to produce specific outputs from specific inputs. These invisible mechanisms manage the greatest flow of information humanity has ever faced. Billions of data points are processed every day. We need the silent but flawless order of algorithms not to get lost in this data stream. They do not just calculate. They decide, prioritize, classify, predict, and sometimes make choices on our behalf without us noticing. Therefore, algorithms are no longer just written codes. They have become the most effective thinking tools of our age. These instruction sets, the invisible workers of the digital world, are a modern reflection of the search for order that humanity has developed throughout history. Every revolution, every civilization has developed new ways to organize chaos. Today, algorithms take on this function. To understand them is not only to understand technology, it is also to decode the way of thinking of our era. Algorithms are not modern inventions. Their roots extend to the oldest mathematical pursuits of human civilization. The idea of generating a solution step by step, which forms the basis of today's artificial intelligence, appears on Sumerian and Babylonian tablets thousands of years ago. Scholars in Mesopotamia developed systematic instruction sets for complex land calculations, debt agreements, commercial transactions, and astronomical observations. These tablets were the first form of algorithms. Operations to be performed were tied to a specific order, and steps were carefully recorded to find the result. Similar methods were seen in ancient Egypt. Measurements, fraction calculations, and geometric rules used in the construction process of the pyramids were early examples of today's algorithmic way of thinking. However, the real great leap in the history of algorithms occurred in ancient Greece, with Euclid's method for finding the greatest common divisor. This method is considered one of the first official algorithms proceeding as a chain of logical steps. Later in the Islamic world, the great scholar al-Khwarizmi introduced systematic operation sequences into mathematical literature, etching the concept of the algorithm into history. In fact, the word algorithm we use today comes from the Latinized form of his name. The methods algorithmic developed on arithmetic and algebra shaped not only mathematics, but the entire future of computational science. These early instruction sets are the cornerstones of the computing world. Even today's complex artificial intelligence systems are still a continuation of this ancient tradition of step-by-step solving. To understand the history of algorithms, one must look at the deep roots of mathematics. Euclid's work, Elements, is not just a geometry book. It is the fundamental reference point for logical thinking and step-by-step problem-solving. Euclid's algorithm for the greatest common divisor is one of the first formalized algorithms in human history. The approach of breaking a problem into systematic parts would later become the fundamental logic in computer science. The person who developed this foundation was al-Khwarizmi. He not only built the systematic structure of algebra, he also laid out clear, sequential, and followable steps for the solution of many mathematical problems. The idea of step-by-step solution is seen in its most refined form in his works. Thanks to this mindset, even complex operations became solvable by following an orderly path. When the methods developed by al-Khwarizmi reached Europe, the doors of a great transformation in the history of mathematics were opened. His work was influential in many fields, from numeral systems to logarithmic calculations. Concepts such as operation sequencing, conditional steps, and dividing into sub-problems, which lie at the heart of computer science today, are modern versions of the logical line of thought developed by al-Khwarizmi. Therefore, algorithms are not only the product of the modern computer age, they are one of the oldest reflections of humanity's mathematical curiosity. Euclid and al-Khwarizmi are the ancestors of all the algorithms we use today. The transition of algorithms into a practical form in the modern sense began with humanity's quest to mechanize logic. This quest transformed from the abstract world of mathematics into a structure transferable to physical machines. Logic gates are the fundamental building blocks of this transformation. When simple-looking logic operations like AND, OR, and NOT found their counterparts in electronic circuits, they formed the foundation of computer science. Because every logic gate is a physical step of an algorithm. In the 19th century, George Boole's development of Boolean algebra established the mathematical model of logic, providing the infrastructure for algorithmic thinking. Thanks to Boole's system, thought processes gained a symbolic language, and this language became applicable in electric circuits. Much later, Claude Shannon's revolutionary work connected logic gates directly to electric circuits. Thus, thought and electric current met on the same mathematical ground. This development allowed algorithms to cease being merely abstract mathematical concepts and turn into systems capable of working in the physical world. Every computer, every phone, Every digital device we use today is a giant algorithmic machine where millions of logic gates operate in sequential steps. Logic gates form the basic computational order of our age by transferring humanity's way of thinking to transistors. Therefore, the story of algorithms is also the story of thought, transforming into a physical form. The true birth of modern algorithms began with Alan Turing, the greatest genius of the 20th century. Turing was seeking an answer to one of the most fundamental questions of mathematics. Can a machine imitate the thinking process? This question shook the foundations not only of computer science, but also of humanity's understanding of intelligence. The Turing machine developed by Turing was an abstract but incredibly powerful concept, showing that thought could be reduced to a mechanical model. This model is the purest form of algorithms, an input and output, a set of states and rules to be followed. Turing etched the concept of computability into history by determining the theoretical limits of what algorithms could calculate. This work is the basic mathematical framework of every piece of software, every application, and every artificial intelligence model written today. During the Second World War, the machine named Bomb, developed by Turing, changed the fate of the war by breaking Nazi Germany's Enigma code system. This success proved that algorithms were far beyond a theory. They had become a tool powerful enough to change the course of human history. Turing's work opened the door to a new era for humanity, the computer age. Today, the foundations of modern computer science are still shaped around his thoughts. The unification of algorithms with the idea of a thinking machine became possible thanks to Turing. While Alan Turing's theoretical model defined how a calculation could be done, John von Neumann paved the way to turn these operations into a real machine. The computer architecture he developed in the 1940s is the fundamental model determining the working logic of all computers we use today. Von Neumann's greatest invention was concreting the idea of the programmable machine. That is, instead of performing a fixed task, a machine became capable of performing different operations according to instructions stored in its memory. This allowed algorithms to be written directly into machine memory and changed when necessary. This architecture is based on three basic components: the central processing unit, memory, and input-output units. This structure makes it possible for algorithms to be executed perfectly within a physical order. Today's computers, phones, tablets, internet servers, and even the most advanced artificial intelligence systems still use the abstracted form of this basic architecture. Von Neumann's model also paved the way to increase the speed and efficiency of algorithms. Access to memory, processor cycles, sequential commands, all are part of the internal structure of algorithms. This architecture, the silent heart of the modern digital world, ensured that algorithms ceased to be merely a mathematical concept and turned into a real technology. Every step the digital world takes today is built upon the foundation laid by von Neumann. When the Internet launched, the greatest information explosion in human history, a system was needed to organize this massive ocean of data. Billions of web pages, interconnected texts, images and links. Algorithms stepped in to guide this chaos. Early Internet architects developed simple but effective methods to manage the flow of information. Link tracking systems, page indexing techniques, and basic routing tables. As the web grew rapidly in the 1990s, Internet algorithms ceased to be just a tool. They became the infrastructure of the information age. Web crawlers analyzed pages, examined links, and added every new site to giant digital maps. This period is the era when algorithms took on the role of digital librarians. As data increased, the role of algorithms expanded. Critical decisions such as understanding what the user is searching for, deciding which information to highlight, which route is the fastest, and which content is reliable, were based on results derived from data patterns observed by computers. The first algorithms of the Internet established the backbone of the information age. They formed the basic order of the online world used by billions today. The entire flow of modern digital life is the evolved version of these early period systems. As the Internet grew, the main problem became accessing information. How would the right information be found among billions of pages? The greatest answer to this question was the ranking algorithms developed by search engines. The most famous of these was the PageRank algorithm, which literally reshaped the Internet. The idea of PageRank was simple, but terrifyingly effective. The value of a web page should be determined by how many pages link to it and how reliable those linking pages are. In other words, the Internet was seen as a giant social network, and links between pages were interpreted as a voting mechanism. The most valuable information was the information that received the most references. This approach revolutionized the way digital information is organized. Information now gained meaning not just by existing, but by its position within connections. In a sense, the real power determining the hierarchy of the Internet was no longer humans, but algorithms. Search engines became the invisible rulers of modern society. They began to largely determine which news would stand out, which products would be popular, which ideas would spread, and which videos would be watched. Today, search is not just finding information. It has become a mechanism determining the rhythm of culture, economy, and society. And at the heart of this mechanism lies this invisible equation that ranks the world. One of the greatest questions of the modern digital age is this: what will I watch? What will I read? What will I listen to? The answer is almost never our conscious choices. Today, most of our decisions are shaped by recommendation algorithms without us even realizing it. The best-known example of these systems is Netflix's personalized recommendation mechanism. When you click on a series, pause, fast forward, or leave an episode halfway and move to a new one. All these micro-movements are recorded in a giant data pool. Recommendation algorithms used on platforms create a unique profile for each user. Some models work with the logic of what did similar users watch, while others analyze features such as genre, cast, and color palette of the content. More advanced systems use machine learning to discover patterns in viewing behaviors. The result? A recommendation list that you think was produced specifically for you, but was actually determined by complex calculations. The impact of these algorithms is much greater than we think. Which content a platform highlights shapes popular culture. When a song climbs to the top of the charts, it is not just because of the artist's success. It is because the algorithm showed it to millions of users. Recommendation systems today are powerful enough to shape not only our entertainment habits, but also shopping preferences, news consumption, social media behaviors, and even political views. In the age of digital streaming, a large part of our choices are directed by an invisible mathematics. The name of this mathematics is recommendation algorithms. Nothing we see on social media is a coincidence. The appearance of a video before you, a post moving to the top of the feed, a friend's content becoming more visible, or some ideas reaching large masses. All of these are the result of the invisible regulating power of feed algorithms. Platforms track every user's behavior at a microscopic level. How long did you watch? Where did you tap? Which content did you scroll past quickly? Which titles did you return to? At what hours are you active? With which content did you interact longer? Each of these data points allows the algorithm to characterize you. Every user carries a unique digital signature. Platforms analyze this signature to present content you might be most interested in, because keeping you on the screen is their primary goal. Social media feed algorithms have now become one of the most powerful mechanisms shaping human behavior. A content going viral, an idea reaching millions, a product becoming popular. Behind all these works, an invisible logic. Feed algorithms are the invisible editors of modern culture. They can even determine what we talk about, what we think, and what the agenda will be. The true architect of the digital age is these algorithmic regulators, most of which we are not even aware of. Classic algorithms were fixed instruction sequences following specific steps. However, in the modern world, data multiplies so fast that these fixed methods began to lag behind. This is where machine learning steps in. Algorithms that learn by themselves, adapt, and can make more accurate decisions over time. At the core of machine learning is extracting patterns from data. An algorithm trains on thousands, millions of examples. Then it discovers the common points of these data and becomes capable of making predictions when new data arrives. Thanks to this, algorithms can predict with great accuracy which photo contains a cat, which sentence harbors anger, what genre a movie poster belongs to, or what a customer will buy. These systems are used not only in entertainment applications, they are also used in disease diagnosis in medicine, risk analysis in finance systems, yield prediction in agriculture, threat detection in cybersecurity, and even in early earthquake warning models. Machine learning transformed algorithms from static instructions into evolving intelligences. The artificial intelligence tools, natural language processing models, image recognition systems, and automated driving technologies we use today are the products of these evolving algorithms. This transformation raises a new question for humanity. If an algorithm is learning, who will determine its limit? As computer science approached the limits of classical computing, humanity turned to new pursuits. This pursuit opened two great doors: quantum algorithms and bioalgorithms. Quantum algorithms draw power from the probability-based nature of subatomic particles. In classical computers, a bit is either 0 or 1. But quantum bits can be both 0 and 1 at the same time. This offers the potential to solve some problems millions of times faster than classical computers. Even now, quantum algorithms have begun to revolutionize fields such as cryptography, material science, and drug design. On the other hand, bioalgorithms are inspired by nature's own processing methods. The way DNA replicates itself, the communication methods of cells, the pattern recognition power of neural networks in our brains, all contain an algorithmic order. Scientists are trying to develop faster, more efficient, and more flexible systems by transforming these natural mechanisms into engineering models. These two fields, quantum and biological computing, represent the future of algorithms. Perhaps for the first time, humanity does not see computing limited only to machines. It reinterprets nature itself as a computing machine. The algorithms of the future will be neither purely digital nor purely biological. Probably hybrid systems combining both will open the doors to a new era. The story of algorithms is not just a technological evolution extending from the past to the present. It is also a profound question shaping our future. Every system, every application, every digital tool we use today is under the influence of an invisible decision mechanism. This mechanism sometimes makes our lives easier, sometimes understands us better than we do, and sometimes silently directs what information we will see, what we will consume, and who we want to be. Therefore, the future of algorithms is not only a technological issue, but also an ethical responsibility. Which algorithms are objective? Which contain bias? Which decisions should remain under human control? Can a decision made by an algorithm determine a human's destiny? These questions are gaining more importance. Loans, hiring, health priorities, legal risk assessments. Decisions once made by humans are now made by algorithms. The stronger these technologies become, the more responsibility we place on them increases. In the future world, a new partnership is born between human and machine. A hybrid era where human intuition, values, and creativity combine with the speed, accuracy, and data capacity of algorithms. In this era, algorithms will not be just calculating tools. They will be partners extending, supporting, and often guiding human thought. Perhaps the real question to be asked is this: will we shape the future of algorithms, or will algorithms shape our future? Throughout history, humanity has sought ways to organize chaos. This long journey extending from the first clay tablets to electronic circuits, from logic gates to artificial intelligence, is actually the story of a single common quest: to understand, organize, and control information. Today, algorithms are the strongest representatives of this quest. They speak the invisible languages of the digital age, find direction within the ocean of data, turn thought into operations, and decisions into numbers. They are the silent architects of the modern world. But their story is intertwined not only with technology, but with humanity. Because every algorithm starts with a human's question. Every system is the product of curiosity. Every innovation is born from the desire for a more orderly world. And perhaps the most striking part of this story is this: we invented algorithms, but today they organize the world. Therefore, if we want to understand the future, looking only at technology is not enough. We must understand how algorithms think, how they decide, and how they shape our lives. Because the power defining our age is now a language consisting of invisible lines. And those who can decode this language will direct the world of tomorrow.